Let's shift our attention from forces by a spring to forces on a spring. So here's a spring hanging from the ceiling supporting a brick, and there's its free body diagram. And in particular, this is equilibrium, and so the vector sum of forces should be 0. If we replace that spring with a softer spring, then one thing is the softer spring ought to also be lighter. There's less metal in it, and so the gravitational force on it should be smaller. But because it's still in equilibrium and the force due to the brick won't have changed, that means the force due to the ceiling will have decreased in magnitude. If we take that to an extreme and find a very strong thread that'll support the brick, now, compared to the forces exerted by the ceiling and the brick, the gravitational force on this thread should be negligible. But if it's still in equilibrium, that means that the magnitudes of the force due to the ceiling and the brick should be very nearly the same. And here's where our approximation comes from, because those two forces are members of interaction pairs. With the ceiling, and that tells us that the force that the ceiling exerts on the thread is the same magnitude as the force that the thread exerts on the ceiling, and the same for the pair of forces to do with the interaction with the thread and the brick. But that then tells us that the force that the thread exerts on the ceiling is about the same magnitude as the force that the thread exerts on the brick. So as long as the contact forces exerted on the ends of something like a spring or a thread are large compared to the gravitational force exerted on it, then the contact forces that it exerts on its ends are approximately the same. So when you pull on one end of a rope with a 100 Newton force and it's attached to a wall, you know that the force it exerts on the wall is about 100 newtons. We say the tension in the rope is 100 newtons, and that's just the magnitude of the forces that both ends of the rope will exert. Similarly, if you pull on one end of a rope with a 100 Newton force and your friend is pulling on the other end, then the force your friend must be exerting is 100 newtons, because the tension in the rope is 100 newtons and the forces exerted at the ends have to be the same. Let's think about this situation of a cart on a table attached to a string which goes over a pulley to a hanging mass, and we'll draw the free body diagrams for both and just think about them a little bit. So what we know ought to happen when we release this whole arrangement is that the cart is going to accelerate to the left because the string is pulling it that way, and the mass ought to accelerate down. So I'm going to start with the free body diagram of the cart, and so I've listed the agents and the forces that they'll exert. The table is just going to push up. And then there will be a gravitational force down, and the string is going to pull to the left. And we already know that the cart accelerates left. Notice that I've made the string horizontal. If I hadn't, this force wouldn't be horizontal, but we certainly expect the vector sum of forces on the cart to be horizontal, and so if this force wasn't horizontal, we could have a rather complicated situation where we still have to get a sum of forces that's horizontal, but that would tell us that the vector sum of forces would be equal to only the horizontal part of the force exerted by the string. So that's why I've put the string horizontal. It's a much simpler situation than this. Now I'll do the mass, and once again I've indicated the agents, and in particular the only contact force is the one due to the string, because that's the only thing the mass is touching. And so it's a very simple free body diagram. And I've deliberately made the gravitational force bigger than the force that the string is exerting because we know that the acceleration of the mass should be down, and so the vector sum of forces should be down. Now the only other thing to note is that because these forces that the string is exerting on the cart and mass are probably quite a bit bigger than the gravitational force on the string, that means that these two forces that the string exerts, one on the cart and one on the hanging mass, should be about equal in magnitude. So here is an example. We have a hiker using a rope to pull their pack up a slope, and the rope is making an angle of 15 degrees relative to the slope, and the slope is 20 degrees above the horizontal, and right now the hiker is pulling with a force of 160 newtons, and the pack is accelerating up the slope at 1.2 meters per second squared. And I've drawn a free body diagram for the pack. There's the gravitational force, a perpendicular force, and a kinetic friction due to the slope, and the force that the rope is exerting on the pack. And what we want to do here is find the strength of the friction force exerted by the slope on the pack. So the first thing I should do is define some axes. And a piece of advice I've given before is that you should always define your axes so that one axis points in the direction of your acceleration if you know the direction of the acceleration. And in this case, that's up the slope. And so I am going to point my x-axis up the slope and my y-axis perpendicular to the slope. Now the next thing I'm going to do before working any further is I'm going to simplify my notation somewhat. These symbols for forces with all the subscripts on them are really good when you're figuring out what forces exist and checking whether you've correctly identified them. But in a case like this where we only have a single object, and so there's a single gravitational force, and in this case a single perpendicular force and a single friction, and so on, the notation is unnecessarily cumbersome. If I had multiple objects, I would probably keep this notation, but I don't. So I'm going to simplify it before I go any further. I only have one gravitational force. I only have one perpendicular force. I only have one kinetic friction. This, well, I could just call it Fc for contact force, but that's awfully non-specific. So because of a tension in a rope, I'm going to call it T. Now it's time to write my equation of motion. And so I'm going to write it as a sum of x components and a sum of y components of my forces. And let me start with the x components. So remember, I've defined my x-axis up the slope, and so I have some x component of t. I have Fk is pointing straight down the slope, and so I just have minus the magnitude of Fk, and then Fg has some x component where I've written plus, although we know this is negative, so there's a negative hiding inside this. And that will all equal max, but ax is just a because the acceleration points straight in my x direction. And so now similarly, my y sum, I'm going to have a ty, I'm going to have an f perpendicular, and I'm going to have a y component of the gravitational force where I've written plus because this is a component. We actually know that component has a negative buried inside it, and my acceleration is straight in the x direction, and so this is 0. The magnitude of that gravitational force is the inertia of the pack times g. And this magnitude of t is, we know, 160 newtons. And so I am going to decompose them. And so I'm going to start by drawing the two triangles. So I've drawn the two triangles here, and I've put the axes here just to remind us which way they are. And in particular, that shows us that both the x and y components of the gravitational force are going to be negative. And it's all just trig now. So for example, I can see that the x component of the gravitational force is the opposite to that 20 degrees. Now, first of all, I know it's negative, so I'm going to put that in right away. And then it's the opposite side to the 20 degrees, and so it's going to be mpg sine 20 degrees. And similarly, now that we know that the 1 is the sine, if you know your trig, you'll realize the other one has to be cos. So I've just pulled my equations of motion down here where you can see them, and I'll now rewrite them using the components that I've found. And note, I'll just circle my unknowns. That's it. And this is the one I want. And I can see that I can solve for it directly out of this equation with no further work. And so I'll just do that. And so I've plugged in the numbers and used my calculator, and I come up with an answer. Let's work a quick example to see some of these ideas. So here's a block on a surface being pulled by a rope, and the rope is at an angle above the horizontal, and it is not accelerating. So the free body diagram would look like this. Here's this force of static friction, and I'm going to say we know the coefficient of static friction. Note, here's a table of coefficients of static friction. You can look these things up. Look, a lot of these are given to two significant figures. You know what? That's nonsense. Coefficients of friction are so unreliable, so complicated, that we never know them to two significant figures. They depend on things like humidity, how clean the surfaces are. They're so complicated they might depend on what day of the week it is and what the experimenter had for breakfast. So you cannot quote them to two sig figs, but they often are anyway. Anyway, let's figure out what the force of static friction is on this block right now. Go ahead, pause the video for a moment and calculate it. Okay, so if you're back, I hope you didn't do something like mu s mg. If you did that, wrong, because what we've just been talking about is that you get it out of the equation of motion. It is just big enough to maintain the acceleration of 0. So we need a vector sum of forces of 0. So I am now going to write the equations of motion for this block. So I have written the equations of motion here, and here I have decomposed the force due to the rope. And notice, if we want to solve for that static friction, which is right here, it's the only unknown in this equation because we know this component of the force due to the rope. And so there we see that we just, as I explained, solve for the static friction out of the equation of motion. It ends up just being, its magnitude in this case, is equal to the x component of the force that the rope is exerting on the block, which is just 4.33 newtons. Suppose we wanted to know instead how hard we would have to pull on the rope to get this block sliding. Now we actually are asking, how hard do we have to pull so that the friction ends up getting to its maximum value? Because if we pull any harder than that, then the block will start sliding. And so the way to do that is to say, okay, let's let that static friction force be its maximum value, in which case that is equal to mu s times the perpendicular force that the surface is exerting. We could now put that into the equations of motion. I'm going to do that, and I'm going to substitute in for the components of this rope force, except remember, we're finding how hard we have to pull, so it's no longer 5 newtons. So here are the equations of motion rewritten that way. We have two equations in two unknowns. I'm going to leave it to you to solve it. I will take a brief pause and I will show the answer that you should get when you solve it. So solving this pair of equations for the magnitude of the force by the rope, you should come up with something like this. And putting in the numbers, I got 8.96 newtons.